Our second method of measuring force will be with a BB accelerometer, which you'll recognize is exactly the same thing as the astrolabe. So when the acceleration is to the right, the BBs will roll to the left, and you can see they're up here at angle theta. The center BB is at the angle theta measured from the vertical. So the vertical is 0 degrees. And this accelerometer can only be used for horizontal accelerations. Here is the BB in the plastic tube when there's no acceleration, so it's just at rest or constant velocity, and the BB will be right below this center point, and the angle theta is 0. The vertical forces are balanced, so Fg is equal to the normal force, and the normal force here is caused by the contact between the BB and the surface of that tube. Now let's suppose that this accelerometer is accelerating to the left, so you're holding it and you're accelerating. The BB is going to roll up this tube to some angle theta. When it does that, the normal force, you'll notice, is now larger than the force of gravity. The normal force has two components. It has a horizontal component, and this is the horizontal force on the BB that enables it to have this horizontal acceleration. The vertical component is balancing the force of gravity. So the vertical component, even as the BB moves up, this vertical component will always stay the same because it's only going to balance the gravity. There's not going to be any acceleration vertically for the BB. Now what if the acceleration is increased? So you're on a ride and it has an even faster or greater acceleration. The BB is going to be at a larger angle theta. The normal force is going to be even larger. But you'll notice that the vertical component of Fn is still equal to Fg, but it's the horizontal component that is bigger, and that increased horizontal force is what enables the BB to have this increased horizontal acceleration. It's because the net horizontal force is bigger than it was before. So what we want to do is come up with an equation to calculate the horizontal force on the BB so that we can know what, if we know this angle, we're on a ride and we see the BB is at some angle like 30 degrees, what does that tell us about the force? That's what we want to know. Well, the horizontal force is just this horizontal component of the normal force. And an expression for the horizontal component is Fn times the sine of theta. So the sine is the opposite over the hypotenuse. So the opposite, because this is our angle theta up here, the opposite is Fnx and the hypotenuse is Fn. So we have an expression here, the horizontal force is Fn sine theta, but we don't know Fn. Theta is something we can measure, but we don't know what Fn is. So we need to find something to substitute for Fn. Well, looking at our vertical forces, those are balanced. So we know that Fny is equal to the force of gravity, which is mg. The y component can be expressed as Fn cosine theta, so that's equal to mg. And then solving that for Fn, we get an expression that Fn is mg divided by cosine theta. So now we can substitute this for our Fn over here, and then we will have an expression in terms of things that we can measure. So I've substituted now the mg over cosine theta for the normal force, and recognizing that sine over cosine is the tangent, which you may or may not have had that in math yet, but sine over cosine is the same thing as tangent of the angle. This is our final formula for the horizontal force. M can be measured, we know what G is, theta can be measured, so we would be able to calculate horizontal force. So to summarize, the horizontal force on the BB is mg tangent theta. That's our big result that we're going to use. And then once we know that force, now we can calculate the acceleration. Horizontal force is mg tangent theta, so the acceleration must be g tangent theta. We can do the same thing for the person. The only difference is you're going to put in the person's mass. So use a capital M instead of a little m if you are calculating the force on the person. And same thing for the acceleration of the person, you need to use the person's mass. Here's an example. A person rides a carousel and holds the BB accelerometer perpendicular to the velocity so that it can measure the centripetal acceleration. The center BB is at an angle of 4 degrees. What is the horizontal force on the person? So our equation for the horizontal force, which we'll call the applied force, is mg tangent theta, using a capital M because we want the force on the person. So mg tangent of 4 degrees gives me an applied force of 0.07 mg. So 0.07 times the force of gravity. If the person's mass is 70 kilograms, what is the numerical value for the force on the person? So we just need to substitute now the values. So 0.07 times the mass, which was 70, times g, which at the surface of the Earth is 9.8 meters per second squared, gives us 48 newtons.